Go ahead and get started. I don't think what we have to cover today is going to, listen up. I don't think what we have to cover today is going to throw you too much. Should be fine. But this does get a little bit tricky, so you need to make sure that you understand the foundations that we lay today so that this will make sense to you once we get into the harder stuff, okay? So just make sure you're paying attention, make sure you understand why we're doing what we're doing here. Just kind of to back up a little bit, we're really just building on what we've been doing, okay? Because what we've been doing is talking about chemical reactions, talking about how to write an equation, a balanced chemical equation for a reaction, okay? Now we're going to use the coefficients in that balanced chemical equation to help us to predict some things, all right? Already we've been predicting if we mix these two things together, what's going to happen, okay? What are the products going to be? Now what we're going to do is something along the lines of, if I mix 1 gram of this with 2 grams of this, then how much of the product am I going to make? And you can actually, you should be able to tell me that by the end of this unit, okay? So stoichiometry is the study of the quantitative aspects of chemical reactions. Do you remember that word, quantitative? Good. Quantitative, quantity. Qualitative is quality, so that's just, qualitative is more of just a description. What's the color? Yeah, we need some numbers with quantitative, okay? So that's what we're doing with stoichiometry. We're very much back into the math part of this class again, all right? So some of you are excited about that, some of you probably not so much. But really what we're back into now is going to be the dimensional analysis, which is why I had you guys reviewing that for the mole conversions we did the other day, okay?
Why don't we do order? Why don't we do this after the dimensional analysis?
You know, we switch up the order every year, and there's always something that we have to stop for a while and come back to. There's just no perfect way to do it. Okay, so stoichiometry is kind of like cooking, all right? It's basically, it's kind of like a recipe, okay? So if you mix a certain amount of the ingredients together, you're going to get a certain amount of your finished product, your cake, your brownies, whatever it is that you're making, okay? So there's a proportional relationship between 2 or more substances during a chemical reaction. And again, a really simple recipe example that I have always used is the recipe for s'mores, okay? So recipe for s'mores is fairly simple, right? Well, I mean, there's some debate there, okay, about the perfect recipe, but we can talk about that. What do you need in order to make a s'more? Okay, so you need 3 things, right? You need graham crackers, you need marshmallows.
Fire.
I guess you don't necessarily need fire, but that's usually an ingredient, right? Here, we need this, right? Yeah, everybody knows what that means now? Yeah, we need heat, right? And then the other thing we need is the chocolate, okay? So those are really I would say the 3 ingredients you need to make a good s'more. If you want to say heat's an ingredient, fine. Heat is energy, so it's not actual matter. I don't know what's happening right now. I don't think I want to know. All right. So those are your 3 ingredients, right? Now, these have to be combined in a specific proportion in order to make the perfect s'more, right? Okay, so we can actually write this like a chemical reaction. Our product is going to be the s'more. Okay? So then what do we need in order to make the perfect s'more? How many graham crackers?
2.
Okay, so probably 2 of the halves of the graham crackers, right? Well, we'll call it 2. That's fine. So we need 2, I'm going to just call this GC, graham crackers, okay? Plus, what else do we need? 1 M. Are we in agreement that we just need 1 marshmallow? I'm assuming we're talking about the big ones, right? Not the little ones, okay? It's important that we define our terms here. I'll say marshmallow, okay? Here's where the debate comes in, okay? How many chocolate pieces do you put to make the perfect s'more? 12. Okay, yeah, that's maybe on the high end of the debate. 12 is a lot. 4. Okay, so now we're talking about the Hershey bars, right? Okay, the Hershey bars with the little squares. You thinking 4? Yeah, sorry, they are rectangles. You're right. To make it a square, I think you need about 4 of the rectangles. Is that right, or do you need 3 of the rectangles? Is it 4? Okay. All right. So we'll say 4 chocolate pieces, and I'll just abbreviate that as CP. Okay? So I just made a chemical equation, right? I mean, that's basically what a s'more is. It's just kind of a recipe for, you combine these 3 ingredients in exactly that amount, and you will get one s'more, right? Everybody following? These numbers out in front, those kind of correspond to a balanced chemical equation, right? Okay, the balanced chemical equation, we're putting, so, the equations that you've been writing have looked more like, copper plus silver nitrate. Yes?
Story said, shouldn't it be plus triangle?
Okay, we can say plus heat. Or actually, if I'm going to do that, let me make this arrow bigger. And then we'll put the triangle over the arrow like that. Okay. Everybody satisfied now? There we go. So this is a chemical equation, right? But it's basically the same thing as this, okay?
Well, that's not balanced.
What's not balanced? Well, actually it is, because the s'more, really, if I wanted to write out the chemical formula for a s'more, it would be, let's see, we'll call it GC2MM CP4, right? See? So there's your chemical equation for a s'more, and that is actually balanced. I just didn't write it out that way, okay? S'more is the common name for this chemical equation, okay? All right. So these are basically the same thing, though, okay? I mean, it's all we're doing here is we're saying if we mix these 2 things together, this is what we're going to make at the end, all right? It's kind of a recipe. And we're saying for every 1 copper we combine with 2 of the silver nitrates, we're going to end up with 1 copper nitrate and 2 silvers, okay? And that's basically what we're saying up here. For every 2 graham crackers, 1 marshmallow, 4 chocolate pieces we combine together, we get 1 s'more, or 1 GC2MM CP4. Okay? Now, what happens, this is kind of leading us to something we're going to get to a little bit later in this unit, but what happens if, let's say that I want to make, a bunch of s'mores, not just 1, but maybe 10, that I'm going to eat all in one sitting. No, don't do that. That's not a good idea. But let's say that I want to make 10 s'mores, and I have 5 graham crackers. How's that going to work out for me? Okay, well, I'm going to have to either make the s'mores smaller, or that's not going to work out for me, right? Because I don't have enough of one of the ingredients. So there are certain ingredients, you might not always have the perfect proportions, and you might run out of one of the ingredients before you run out of the other. Do you think that happens sometimes in a chemical reaction? Do you think maybe if I didn't put enough copper into this reaction, I might run out of copper before I run out of silver nitrate, and that would limit how much of this can be made? It's basically the same thing, right? Okay. So later in the chapter, we're going to talk about limiting reactants and what that means exactly. I'm just kind of giving you a preview of that. But I want you to keep that s'mores idea in your head, because I think, or really any recipe that you really like, because remembering that a chemical equation is basically just like a recipe, I think helps to make it a little less intimidating sometimes, because sometimes the chemical equations do look a little intimidating. All right? Okay, so there is a proportional relationship. Calculations can be used to predict the amount of a product that would be produced from a certain amount of reactants. Okay, and that's what I said before. by the end of this chapter, I will be able to tell you, you're starting with 1 gram of this reactant, 1 gram of this reactant. You'll be able to tell me how many grams of the product you're going to make. Okay? Or I'll be able to tell you, you've got 1 gram of this reactant, how much of the product can you make? You'll even be able to tell me that, okay, assuming that you have enough of the other reactant. So moles are a key part of this process, all right? Now, I don't know if you remember this or not. I probably shouldn't have erased this formula yet. Let me put this back up here. We talked about this at the end of the last unit. And the reason you may not remember it is because it wasn't even on the test. These numbers right here. Do you remember me telling you that that actually tells you a mole ratio of one thing to another? You don't remember me saying that? Okay. Like I said, we talked about it at the very end of the chapter, so it may have kind of gone by you. But basically what this is telling you is, if I combine 1 mole of copper with 2 moles of AgNO3, silver nitrate, I'm going to produce 1 mole of copper, or sorry, 1 mole of copper nitrate and 2 moles of silver. Okay? It's telling me a mole ratio. All right, so you just have to keep that in mind. These numbers in front, you can think of those as moles now. Okay? And what that means is, if I have 1 mole of copper to start out with, I'm going to end up with 1 mole of copper nitrate at the end. That's a 1-to-1 ratio between these two things. All right? So we're going to talk a little bit about how to figure out mole ratios. Balanced chemical equations give us the relative number of moles of each substance we need for the reaction to work. Okay? So it's basically telling us how much of each reactant we need. And this is a really important concept to understand for the rest of stoichiometry. And this is going to come from the coefficients. Okay? So the balanced chemical equations, that coefficient in the balanced chemical equation tells you the mole ratio. And you can form ratios between any two things. Each of the reactants, a reactant and a product, both of the products, however you want to do this. And this will make more sense once I actually show you an example. I'm just explaining it in words right now. Okay? This is going to be written as a fraction, and it's going to be used as a conversion factor. You guys remember what I mean when I say conversion factor? Okay, that's a conversion factor, right? 1 foot equals 12 inches. But the way that we've been writing it for most of the year, let's say that we want to go from 2.5 inches to feet. The inches on the bottom, feet on the top, 12 inches and 1 foot. This is how we usually write our conversion factors, right? Okay, and that allows us to get from one unit to another. Okay? All right, so here's an example. We've got 2HGO yields 2Hg plus O2. And the question here is that you have underneath that equation, what are all the possible mole ratios using that balanced chemical equation? Okay? So, let's say that I'm looking at HGO and HG. I'm comparing those two. What's the mole ratio of HGO to HG? It's 2 to 2, right? You guys see that? Okay. HGO to HG is a 2 to 2 relationship. So again, remember, we're writing these as conversion factors. So that first relationship, I would write as 2 moles of HGO over 2 moles of HG. Okay? That's one of my relationships there. Now, could I write that in the other direction? Could I flip this? It'd be the same thing, right? It would be like writing this, you know. Can I write it that way as well? Sure. It's the same thing. Now, it just depends on what situation I'm in, right? If I'm going from inches to feet, then I need inches to be on the bottom. But if I'm going from, 2.5 feet and I'm converting to inches, then I would want to use this conversion factor. I'd want feet to be on the bottom, inches to be on the top. Okay? So this is really, these are the same, but I would use them in different situations. Okay? So same thing here. 2 moles of HGO over 2 moles of HG, I might use in one situation, or I might use the 2 moles of Hg over 2 moles of HGO. Okay? It's basically the same ratio, but I would use them both in different situations. All right? So that's one of my mole ratios that I could make here. Okay? What's another one? Just looking at the equation.
2 HCl to 1 O2.
Right, I could compare the HGO to the O2, right? So I could say, sorry, I'm getting kind of close to the bottom here. 2 moles of HGO will produce 1 mole of O2. Okay, and again, I could write that the other direction. 1 mole of O2 over 2 moles of HGO. Okay? And there's one other relationship that I could have here.
2 Hg.
Okay, we could compare the Hg to the O2, right? We haven't compared the two products to one another. Yes, ma'am. Oh, yeah, sorry. They are peroxides. Is that better? Okay. All right, so then the other relationship here, I could say for every 2 moles of Hg that I produce, I'm going to have 1 mole of O2. And again, I could write that, wow, down at the bottom it's not aligning very well, sorry. That's very ugly. I could write that in the other direction as well, 1 mole of O2 produced for every 2 moles of Hg produced. Sorry. That's not my fault, I promise. Other than the fact that I'm writing so low down on the board, that's my fault. Okay, but what I've done here is I've basically just taken this equation and I've made a whole bunch of different conversion factors from the equation. All right, now what do we use conversion factors for? What did I use it for up here? I use conversion factors to, say it again? Yeah, to change the unit, to convert, right? Conversion factors convert. They change from one unit to another, okay, or from one thing to another. So that's ultimately what I'm going to use these for. I'm just making a bunch of conversion factors here, okay? Now, I'm not going to need each of these every single time, but I'll show you an example of when I would need something like this. Everybody have this written down? Okay. Whoops. Here was the question. All right. Another example here. And same question, right? Wait. This looks like a different example than the one that's in your notes. Yeah, I mean, this is basically another example, but it's very similar to the last one. Do we need to talk about this? You guys are okay here? Okay. So let's go on to the example you have in the notes. So first thing that you need to do on this one is balance the chemical equation, and then I want you to identify all of the different mole ratios just like we did on the last one. Okay? So to balance this equation, what would we need to do? To where? To here? And then a 3 here? Well, you don't have to put anything, or you can just put a 1, whichever one you prefer. If you don't like to leave this blank, put a 1. Okay? All right. So there's your balanced chemical equation. Now that's telling us the number of moles of each of these that are in the equation. Okay? So now we can identify all the mole ratios. So what are the mole ratios here? We could compare the Al to the bromine first, right? It doesn't really matter what order you do this in, okay? Yes, it is Br2. All right, so we can say 2 moles of Al need to react with 3 moles of Br2. And I hope you notice how I'm saying this, right? Because these are both on the reactant side. So what this equation is telling me is I need 2 moles of aluminum to react with 3 moles of bromine to make 1 mole of the product. Does that make sense, the way that I'm saying it? Okay? So 2 moles of Al with 3 moles of Br2. And again, you can write that in the other direction. I don't know that it's necessary for you to write it in both directions every time. I just want to show you it can be written both ways because you're going to need to write it in both ways at certain points. Okay? What's another ratio? And I'll write these up here so that you guys can actually see them. What's another ratio we need to think about here? Okay, so we'll compare the aluminum to the product, right? So the way that we would say that is if 2 moles of aluminum react, we're going to make, or 2 moles of aluminum can make 1 mole of Al2Br6. Okay, that's not 2 moles of aluminum by itself. It has to react with the bromine. But and then same thing here. We can switch this. And then what's the one other relationship that we have to pay attention to here?
3 moles over 1 mole Al2 Br.
Yep. So 3 moles of Br2 can produce 1 mole of Al2Br6, and vice versa.
Are we still going to have to like use the like
well, okay, so here's a really nasty problem you could be given. The nasty problem you could be given would be I give you a word equation in a paragraph form. And in that word equation, I tell you the 2 things that I'm mixing together, the 2 reactants, and I tell you the amounts of the 2 reactants. Then you would have to write the equation, figure out what's going to happen as far as products are concerned, and then predict how much of the product gets formed based on those reactants. No, absolutely not. We're going to work up to that. That would be at the very end of this unit. It may not even happen, but I'm telling you that's about the nastiest problem you could see. All right? Yeah, that is. It probably just depends on my mood. So you guys should bring me nice stuff, to eat throughout this unit. And no, I'm just joking. Don't bribe me. I don't accept bribes, unless it's money. No, I'm just joking. All right. Okay, so these ratios can be used in all stoichiometric calculations. When 2 substances in a chemical reaction are discussed within a problem, you would use the mole ratio between those 2 substances. All right? So I just wanted you to be able to look at an equation and figure out all the mole ratios. You're only going to use one of those mole ratios in any given problem. All right? So here's the way that this works. This is where it gets a little bit tricky. All right? And this is as far as we'll probably get today. Commercial preparation of ammonia, which is the reaction between hydrogen and nitrogen. How many moles of hydrogen are needed to prepare 312 moles of ammonia? All right, so here's what we're saying on this one. We are preparing ammonia, okay? So ammonia is our product. Everybody okay with that? That's what we're actually making, okay? Does anyone remember what the formula for ammonia is? Okay. I'm getting a lot of different answers here. Okay. All right. NH4 plus is hang on. NH4 plus is ammonium. Okay. NH3 is ammonia. Okay. All right. Now, you need to hear me when I say this. This is maybe the most important thing I will say in this unit. You ready? Before any stoichiometry problem, the thing you need most of all is a balanced chemical equation. Okay? You cannot do stoichiometry without first having a balanced chemical equation. So we need a balanced chemical equation here. We don't have one, right? So let's make one. All right. So NH3 we know is going to be our product. That goes to the right of the arrow. That's where products go, right? And it says that this is the reaction between hydrogen and nitrogen, right? So there it's telling us our two products, or sorry, our two reactants. Okay, how do I write my two reactants here? H2 plus N2. Everybody okay with that? Why the twos? They're both diatomic, okay? Is that balanced? I need a balanced chemical equation, all right? Well, yeah, it wouldn't be, would it? So I'm going to balance the nitrogen first. Everybody okay with that? Because I've got this weird odd even thing going on with the hydrogen. I want to save that for the end and see if it takes care of itself. So if I put a 2 in front of the NH3, okay, and then I put a 3 in front of the H2, that should take care of everything, right? Now I've got 2 nitrogens on each side. I've got 2 times 3, 6 hydrogens. 3 times 2, 6 hydrogens, okay? So now we have a balanced chemical equation, okay? Now, the question here is, how many moles of hydrogen are needed to prepare 312 moles of ammonia? They want to know how much hydrogen do I need to prepare that much ammonia, okay? So, I've got 312 moles of ammonia. That's what I know at this point. Feel free to abbreviate moles as MOL. It will save you a lot of time. I'm just joking. It'll save you a little bit of time, but, 2 letters. Not much of an abbreviation. 312 moles of NH3. Essentially what I need to do here is I need to convert that into moles of hydrogen, right? So we're doing a dimensional analysis problem here. I'm starting with moles of NH3, so that's what's going to go on the bottom of my conversion factor, moles of NH3. What's going to go on the top of my conversion factor? Moles of hydrogen, right? That's what I'm trying to figure out. Well, if only I had a way to figure out the ratio between the moles of hydrogen and the moles of NH3. It's not 6.02 times 10 to the 23rd. That's if I'm going from moles to atoms. That's why I need a balanced chemical equation, right? Okay? So what that's telling me is I need 3 moles of H2 for every 2 moles of NH3 that I make. It's a 3-to-2 ratio. See that? Okay? So I'm just using that as a conversion factor to get me from one to the other. Moles of NH3 cancels out. Yeah, I forgot about that, didn't you? Okay. 312 times 3 divided by 2. And then we're going to end up with, I don't know how many moles of hydrogen. Let me work this out.
468.
468. That is how many moles of hydrogen I would need to make 312 moles of ammonia. Yeah, it's not that bad. Well, good. Okay, that makes sense? Everybody with me? Okay, so let's use that same reaction we just wrote, which I'll rewrite it here. I think I wrote it in a different order, but it doesn't matter. So here's the questions, okay? You started with 6.78 moles of nitrogen. How many moles of ammonia could we produce? Okay, so now we're starting with the reactant. We're trying to figure out how much of the product we could make, all right? So we are given 6.78 moles of nitrogen. This is on your sheet, isn't it? Yeah, well, you have an actual space for this, which is nice. Okay, so 6.78 moles of N2. We need to convert from moles of N2 to what? Yeah, moles of ammonia, right? Which, again, is the NH3. What's my ratio on that one?
2-to-1.
Everyone in agreement there?
Yeah.
2 moles of NH3. Again, you're just looking at the balanced chemical equation. it takes 1 mole, the way that you would say that is it takes 1 mole of nitrogen to make 2 moles of NH3, right? Okay, so all you're doing, 6.78 times 2. Oh, what's happening in my calculator? All right, this is a good spot to stop and talk about significant figures again for just a second. 13.56 is the number my calculator is giving me. How many sig figs do I need in this particular answer? 3, right? I started with 3 right here. Now, I guess we should say these don't count. These are exact numbers, right? So remember, exact numbers have infinite sig figs. So you don't count these. You just look at the first one, the one you start with, okay? So we need to round it to 3 sig figs. So 13.56 would need to go to 13.6. And that's moles of NH3. All right? And then the last one here, if you needed to prepare 350 moles of ammonia, how many moles of hydrogen and nitrogen would you need? Okay, so we're going to have to take these one at a time, right? So 350 moles of ammonia. I'm just writing it up here so you guys can see it. What do you want to do first? Okay, sure. We'll do the hydrogen first. That's the first one they list, so that makes sense to me. And the ratio here is 3 to 2. And again, I get that from the coefficients in the equation, right? 3 moles of H2 for every 2 moles of NH3. Okay? That's going to tell me how much H2 that I need. Then I'm going to have to do the exact same thing again with the nitrogen. Okay? Now the nitrogen, you might be able to do the nitrogen in your head. Okay? You do have to look at sig figs. So 350 times 3 divided by 2 gives me 525. Well, okay, so we've got 2 sig figs here, right? So we've got to round that to 530. Now, can we do the other one in our heads? So I've got 350 moles of NH3. Based on the ratio, how much N2 would it take? If this is a 2 to 1 ratio, how much nitrogen would it take? It would either take twice as much or half as much. What do we think? Okay, we can always set this up, right? If you're confused, just do your dimensional analysis and that's fine. I'm just trying to give you another way to think about it, okay? Does it make sense that it would take half as much nitrogen to make the NH3? Because for every 1 mole of this, you end up making 2 moles of the product, right? So it would take half as much, okay? But, you know, if you get stuck, yeah, if you get stuck, just work it out, right? See, and that shows you the exact same thing. Oh yeah, we divide by 2. Yeah, see, it's a 1 to 2 because. Yeah. Now we're going to have to round this one also. It's not going to be 175 because that would be 3 sig figs. It would have to be 180, right? And again, that's because there's only 2 sig figs in our first number here, right? So 180 moles of N2. Okay? We are done. I'm going to give you a worksheet here. Yeah, that's it. We're not going on to the gram stuff yet. I'm going to give you a worksheet that has 5 practice problems on it. I don't know that you need a ton of practice here. There is going to be a little quiz on this tomorrow, but again, you guys should be fine, okay?